Hello and welcome. My name is Malte Platoon. I work in the Department of Fiber Photonics, where we investigate light-matter interaction on the microscopic scale by using 3D printed nanostructures.
Hello, I'm Jisoo Kim. We are going to introduce how to research from fabrication to measurement by using 3D printer, which is Nanoscribe. This is Nanoscribe machine. So it is based on commercial microscope here and 780 nanometer pulsed laser in here. And there is computer and interface to control all setup. So I already prepared a sample with photoresist resin. So using this, the laser can be printed by polymerizing. So we can create what we have, what we want. So when I insert the sample, fix the holder, I approach the sample to the objective, so we can clearly see the surface like this. So when I move the joystick, we can move what you want. So when you find the proper position, using the program, we can start the printing. So this is the example which is logo of IPHD. So this is big, but we can create the structure as fine as we want. So in our case, our structure resolution is around 300 nanometer. So this is a transmission setup for checking the liquid state spectroscopy in sample. So I fabricate the light cage sample with V-group chip. So we fabricate a special silicon wafer which is V-group. So there is a V-group, and we print the light cage. So fiber can couple with laser light, and then fiber can couple with light cage. So from output, we can check the CCD core mode image and spectroscopy. Using the output from the light cage, we can check the spectroscopy by using optical spectrum analyzer. So from 400 nanometer to 800, when I sweep the spectrum, we can see clearly special feature from the light cage. So we have checked spectrum, and we can also check the core mode image from the CCD camera. We moved the setup to the microscope setup because this is a setup for nanoparticle tracking. So I put the nanoparticle solution, which is from 30 nanometer to 80 or 100 nanometer. So using this light cage, we can see clearly nanoparticle Brownian motion. So nanoparticle scattered to microscope, and we can immediately observe the nanoparticle brightness. So we can estimate the nanoparticle size using this.
Using the Nanoscribe, we fabricate a meta lens that is based on the diffractive principle onto the facet of an optical fiber. We use this for particle trapping, and in particular it requires a numerical aperture of greater than 0.8. This aperture allows us to trap individual microscopic particles and even bacteria in a water environment by using just one single fiber. In this setup, we have built up a laser that is deflected with two mirrors into this optical fiber, and on the facet of the optical fiber we have the printed meta lens. On the screen you can see an image of the diffractive lens that we use for the particle trapping. To observe the particle trapping, we have here a microscope that consists of an illumination part and an observation part to observe the motion of the trapped particles. After the light is coupled into the fiber, we insert the fiber into a printed chamber that consists of two parallel microscope cover slips that allowed to create a small thin film of liquid solution in between. On the screen we can see the fiber that is inserted into the chamber, and we can then move around the fiber to find it under the microscope. You can see here that the black area or the dark gray area represents the lens on the fiber, and on the bottom the white lines indicate the boundaries of the fiber. If I move the fiber now to the center of the screen, we can see the scattered light that leaves the fiber, which we can increase or decrease a little bit so it doesn't disturb the observation. We then wait until the particle moves in front of the fiber, which is then there trapped. The ultra-high numerical aperture of the meta lens that is printed on the optical fiber, which we call a metafiber in combination, allows to just trap one single particle in the focus. The focus is approximately 50 micrometer in front of the facet. The focus is so small that once the second particle enters the focus, the first particle that was in there is immediately kicked out. We demonstrate the optical trapping of the particles by moving the fiber left and right and up and down to demonstrate that the particle is trapped in a non-contact mode. We did the same demonstration with E. coli bacteria that have roughly the same size but experience a completely different shape. They are longitudinal in shape, which shows that the fiber not only allows to trap spherical beads but also biologically relevant objects of interest. The first videos allowed us to qualitatively investigate the behavior of the trap. To quantitatively assess the performance and compare it to other optical trapping based approaches, we record the video of a microscopic particle in the trap as a zoomed in version. Here we record the Brownian motion, which means the rapid movement of the particle inside the trap, over times of several minutes. The particle is confined here at a power of 30 milliwatt and is stably trapped in the center, which means it doesn't leave the frame for these minutes. We then use an image tracking algorithm to retrieve the motion of the particle frame by frame and investigate the trajectory. The trajectory then allows us to obtain information about the stiffness of the trap, which means how tight is the particle confined. We can do the same for the E. coli bacteria that are also stably trapped in front of the optical fiber for several minutes. Here, we don't retrieve the exact position for a quantitative analysis because we expect them to be as tightly trapped as the spherical silica beads. An analysis of the longitudinal shaped bacteria requires a much more complicated tracking algorithm because, as you can see in the video, this also would require the rotational diffusion in addition to the diffusion along the three spatial dimensions. I hope the quick demonstration gave an insight into the work that is done in the Department of Fiber Photonics. You can find many interesting recent publications, for example for the light cage in analytical chemistry and for the ultra-high numerical aperture metafiber-based optical trapping in light science and application. Thank you.